Going live. Okay, I think we are live. So hello everyone and welcome back to the Latin American webinars on physics. Even though you cannot see me, I am Joel Jones from the PUCP in Peru, who is having a day with a bad connection, but I will be your host today. So this is webinar 142, and we're having Kevin Hinze as a speaker. Kevin is currently a third-year PhD student working at the University of Basel under the supervision of Stefan Antush. Today, Kevin will give us news about SU5 grand unified theories, as well as its connection to Axion dark matter, and we are very happy to have him as a speaker today. So before we begin, let me remind the viewers that you can ask questions and make comments via the YouTube live chat system. And these questions will be passed on to Kevin at the end of his talk. So, okay, Kevin, please share your screen. Excellent. Everything good.
So thank you, Joel, for this kind introduction, and thanks also for this great opportunity to present my work here at lawphysics. So this talk is actually based on these 4 publications here that have been worked on in collaboration with my supervisor, Stefan Antush, and then Sheikh Saad, and recently also with Ilya Dorshner. So unification is actually an idea which has been around for quite some time in physics. Here are some examples of unification. Already in the 17th century, Isaac Newton proposed a unification of celestial and terrestrial gravity. Then, even more impressive, in the 1860s, there was a unification of electricity and magnetism, which resulted in Maxwell's equation and also allowed to describe light as an electromagnetic wave. And more recently, at the beginning of the 20th century, with Einstein's theory of relativity, a unification of space and time was achieved, and also a unification of mass and energy. And this maybe also led to the most famous equation of physics. Then in the 1960s, with the invention of the Higgs mechanism, a unification of QED and the weak nuclear force was achieved. So naturally, some physicists wonder whether this concept of unification can be brought into other aspects of physics. And one idea which goes in this direction is actually the idea of grand unified theories. In a grand unified theory, we would have a unification of the electroweak and the strong nuclear force at some very high energy. Now, what are the motivations of such a grand unified theory? If we look at the standard model gauge couplings and we run them up to a very high energy, then they come very close, which is not something which one would expect. I mean, they could also drift apart or just run parallel, but they come very close. And if we maybe have some additional threshold corrections, it could also be possible that with these new corrections that they unify in a single point. And if this is the case, then this could be a hint for a grand unified theory. Then apart from this, there are also other motivations to have a grand unified theory. First of all, the Fermian content of the standard model is quite complicated. I mean, we have 5 different representations for each family of fermions, and yeah, they live in sort of strange representations within a GUT can be simplified. So, for example, in SU5 guts, one only needs 2 different representations per family, or in other higher gauge groups, such as SO10, a single representation could embed all the standard model fermions of one family. Then, moreover, in the particles which we observe, for some reason, seem to have a quantized electromagnetic charge, which is not something which one would expect, right? I mean, the hypercharge is just some U1 factor, so we could expect some very strange charges, such as square root of pi or whatever. But for some reason, the electromagnetic charge is quantized. And this can also be explained by a grand unified theory. On top of that, in the standard model, gauge anomalies just randomly cancel, and they just cancel for each family separately, just because of the matter content that we have. And what's also interesting is, in order for these gauge anomalies to cancel, one really needs quarks and leptons together. And yeah, all these things can be explained more naturally within grand unified theories. Okay, now to the outline of my talk. I will start with SU5 guts. So the minimal SU5 gut model, which was proposed by Howard Chorchai and Sheldon Glashow. And I will also discuss the shortcomings of this model. Then I will present an approach to build realistic gut models, which also predict fixed quark lepton Yukawa ratios at the gut scale. Then I will turn to the strong CP problem and discuss the Pechi-Quinn solution to it. And last but not least, I will show you how this Pechi-Quinn mechanism can be combined with SU5 guts. Okay, let's start with the Chorchai-Glashow model. So in the Chorchai-Glashow model, the standard model field content is embedded into two generations of representations under SU5. So in this 5-bar representation, we have the right-handed down type quarks as well as the left-handed lepton doublet. And then in the 10-dimensional representation, we have the right-handed up quarks, the left-handed quark doublet, as well as the right-handed electrons. On top of these fermions, we introduced 2 scalar fields. One lives in the 24-dimensional representation, which is the adjoint of SU5. And this is needed to break the SU5 gauge group down to the standard model gauge group. Moreover, the electroweak Higgs doublet is embedded into a 5-dimensional representation of SU5. And the web of this fields then is responsible for the electroweak symmetry breaking, which we also have in the standard model. Okay, let's look at the Yukawa sector of this model. So with the field content and the gauge symmetry, there are actually 2 Yukawa couplings which are allowed to write down. One is this coupling with 5-bar, 10, and the 5 Higgs. And then there's another coupling with 10-bar, with 10, 10, and 5 Higgs. So from this first coupling, once the gut symmetry is broken, we obtain these 2 standard model Yukawas. And then from the last coupling, we obtain the up-type Yukawa matrix. And then we obtain these 2 predictions. So here we can see the up-type Yukawa matrix is actually predicted to be symmetric. And for the down-type quarks and charged leptons, we have this relation that one is the transpose of the other. This in particular also implies that the singular values of these 2 matrices are unified. So this is actually a quite nice prediction at the qualitative level, because it explains why the charged lepton masses and the down-type quark masses are so similar. However, on the quantitative level, it's just not true. We can see this by taking the observed values at low energy and running them up to high energy. So here the red curve represents the second family, which that means the mu Yukawa coupling is divided by the strange Yukawa coupling. And if we run this up to a high scale, this is roughly equal to 4.5. And then for the third family, here represented in blue, so the tau Yukawa coupling divided by the bottom Yukawa coupling, if we run this up to high energy, this is roughly equal to 1.5. And obviously both of them are far away from 1. So one natural question which one can ask is whether such ratios like 4.5 or 1.5 can be explained in a gut. This is something which I will turn back in a few minutes. Okay, then neutrino masses, this is another problem of the Church-Glashow model. The Church-Glashow model predicts massless neutrinos. This is simply because we don't add any singlets or anything else which could give neutrino masses. However, the problem in SU5 is even worse than in the standard model, because in SU5, if we want to write down such a Weinberg operator, a dimension 5 operator, then this has to be suppressed by some scale which is larger than the gut scale. And with this, we predict neutrino masses which are too small. So that means we cannot solve the neutrino mass problem with higher dimensional operators, and we should solve it differently. Okay, then there's also a third problem of the Church-Glashow model, but before I can come to that, I first want to discuss how the gauge bosons are embedded in SU5. So here we have 24, so the gauge bosons are embedded in a 24-dimensional representation. And this would be the gluons. This would be the W bosons of SU2 left. And hypercharge is embedded here on the diagonal of this 24-dimensional representation. But since the adjoint of SU5 is 24-dimensional and the standard model only has 12 gauge bosons, we have to introduce these 12 additional gauge bosons on top of the standard model field content. And these additional gauge bosons are actually both leptoquarks and diquarks, and because of this, they can lead to proton decay. Then, moreover, once the gut symmetry is broken, these additional gauge bosons obtain a mass, which they get by eating up some scalar field, some scalar freedom field. Okay, so how does proton decay work? As I said, these gauge bosons are both diquarks and leptoquarks, and then we can have processes like this where proton can decay into a anti-lepton and a meson. And with a dimensional estimation, we can find that the mass of these leptoquark of these gauge bosons has to be larger than 10 to the 15 GeV, and this also means that the gut scale has to be of this order, and this is something which cannot be realized within the Church-Glashow model. So this is actually a third problem of this model. Okay, an intermediate summary of all the shortcomings of the Church-Glashow model. So first of all, unification cannot appears at a scale which is too low, which means that proton decay is actually predicted too rapidly. Then we predict massless neutrinos. And thirdly, we have a wrong prediction for the Yukawa matrices. Now, how can we solve all these shortcomings? So for the first two, one just needs to introduce additional fields. And if some of these fields have intermediate scale masses, which means between the electroweak scale and the gut scale, then these two problems can often be solved simultaneously. Okay, let's look a bit deeper into the neutrino problem. So actually in the standard model, we have 3 solutions to generate neutrino masses at tree level, and all of these solutions can also be embedded into SU5. So if we just introduce right-handed neutrinos, we can have a type 1 seesaw mechanism, same as in the standard model. Then for the type 2 seesaw mechanism, one needs a SU2 triplet scalar field, and this lives in the 15-dimensional representation of SU5, which means if we introduce this 15-dimensional representation, we can have a type 2 seesaw mechanism. And then the adjoint representation contains a standard model singlet as well as a triplet under SU2 left. And therefore, by introducing such an adjoint fermion field, we can have a hybrid of a type 3 and a type 1 seesaw mechanism. Moreover, there are several solutions to produce neutrino masses at the loop level. One of these solutions I will discuss later in my talk. And for the bad mass relation, I will discuss on the next slide some solutions. Okay. One very straightforward solution is just to allow for any higher dimensional operators, and with this sort of just destroy the prediction. This is maybe a solution which is not so nice, but it works if one wants to allow for all higher dimensional operators. Then a second solution would be to introduce vector-like fermions, which are which then mix with the standard model fermions and thus interplay with the mass relation. I will discuss one such solution later in my talk. Okay, and then there's also the possibility to have a second Higgs doublet, which is embedded in a 45-dimensional Higgs field, and another solution which is called single operator dominance. I will discuss both of them basically now. Okay, so let's say we have the standard model, we have the Church-Glashow model, and we add an additional 45-dimensional Higgs field. Then we can write down an additional Yukawa coupling. Okay, we can also write down other things, but we are now interested in this additional Yukawa coupling. And with this additional Yukawa coupling, we get then a different mass relation where we have this factor -3. And that means what we could do is we could consider linear combinations of these two matrices. And with this, we would have enough freedom to fit everything. However, if we do this, then we sort of lose some predictivity in the Yukawa sector. So one idea which was proposed by Chorchai and Yarlskog was that if an additional family symmetry is introduced on top of the gauge symmetry, then it's actually possible that different generations of fermion fields couple to different Higgs fields, and therefore we can have different different relations for different entries of the mass matrices. So they actually proposed such a texture for the mass matrices, and in this case, only the 2-2 entry is generated via a coupling to the 45-dimensional Higgs field, while the other couplings, the 1-2, the 2-1, and the 3-3, are all produced by a coupling to a 5-dimensional Higgs field. And if the mass matrices are of this form, then we get other ratios. Namely, for the third family, we get a ratio of 1. For the second family, we get a ratio of -3. Both of them are directly coming from these operators. And then for the first family, from the diagonalization of this matrix, we would get a factor of -1/3. Now, this model is quite old, 1979. At this time, these ratios were working, but with the current data, this is a bit outdated, as we have already seen before. I mean, for the third family, a ratio of 1.5 is working much better than 1, and for the second family, a ratio of 4.5 is working much better than 3. So the question arises, can we get such factors, let's say 1.5 and 4.5, out of some gut operators? And this question was actually answered by Stefan Antusch and Martin Spinrad, if one allows for higher dimensional operators. So what they did, they were considering higher dimensional operators of this form, and 2 of these external fields have to be standard model fermions. So these have to be such fermion fields, and the other 2 have to be Higgs fields, one of which gets an electroweak scale VEV, and the other one gets a gut scale VEV. Then here we have heavy messenger fields. They should have masses above the gut scale, but below the Planck scale. And lambda just shows how the messenger fields obtain their masses. So this could be a singlet mass term, just writing down a bare mass term, or this could also be a mass term which is effectively generated via a coupling to the adjoint Higgs field. And if we then look at the Clebsch-Gordon coefficients of such operators, then we actually obtain Yukawa ratios. So here are a few examples of such operators. Such an operator here, where we have a 24-dimensional Higgs field, a 5-dimensional Higgs field, and the messenger is also 5-dimensional, and something like this could give us a ratio of 3/2. And if we replace this 5-dimensional Higgs field with a 45-dimensional Higgs field, then we can get a ratio of 9/2. Then here in this example, it's important to note that this is actually also a dimension 5 operator, not dimension 6. This 24-dimensional Higgs field here just indicates that the messenger field get their masses via a coupling to the 24-dimensional Higgs field. And an operator, a diagram like this can give us a ratio of 2. And this last diagram here can give us a ratio of 6. All of these ratios will be important in the following slides. Okay, but it's not, of course, nice to have these operators, but if we have a given model, how can they predict, let's say, Yukawa ratios? So first of all, the Yukawa matrices have to be hierarchical. And secondly, the 3,3 and 2,2 entries need to be dominated by a single operator. So that means if we have the SU5 gauge symmetry, then we need to add an additional family symmetry on top of it, which ensures that this 3,3 entry and 2,2 entry only comes from a single gut operator. Similar as in the case of the Georgi-Yarlskog model. Okay, what we have done is we have investigated a few gut scenarios where the neutrino masses are generated via different mechanisms, and we have for each of them investigated the viability of such fixed gut ratios. So in the first scenario, we have added 1-dimensional fermion fields as well as a 45-dimensional Higgs field on top of the Georgi-Glashow model. Then these one-dimensional Fermion fields allow to write down neutrino masses or via a type 1 seesaw mechanism. So this works exactly the same as in the standard model. And then the 45-dimensional Higgs field allows for gauge coupling unification. And it also allows to write down an operator giving this ratio 9/2. Okay, now if we look at the running of the standard model Yukawa matrices, we actually see that this gets changed by the new neutrino, by the new Dirac coupling for the neutrino. And what's particularly important is this term here, which indicates that the running for the charged lepton Yukawa matrix is slowed down if we have this Dirac Yukawa matrix. So you can see it in this plot. If the Dirac Yukawa matrix has entries which are much smaller than 1, then we get the same running as in the standard model. But if these couplings are of order 1, then this can slow down or even reverse the running. And with this, it's actually possible to obtain a ratio of 1.5 at the gut scale. Okay, so let's say we have the ratios 1.5 for the third family and the ratio 4.5 for the second family. Then there are quite a few possibilities to build full models which have this property. And one question which one can ask oneself is how to distinguish between all these possible models, which all have the same property. So what we have done is we have just analyzed 2 toy models, and we have shown that they have quite different predictions for the Nucleon decay. So in this first model, the downtype and charged lepton Yukawa matrix have a non-trivial 1/2 block, and the uptype Yukawa matrix has 0 entry in the 1,3 and 3,1, and it's also a symmetric matrix. In the second model, the uptype Yukawa matrix is a general symmetric matrix, and the downtype Yukawa matrices and charged lepton Yukawa matrix is diagonal. Okay, and what we have then found is if we consider the predictions for Nucleon decay and we take 2 different decay channels and compute their ratios, then they have quite different predictions. So if we, in the very far future, are able to measure these ratios of different Nucleon decay channels, then we could distinguish between, at least between these 2 models. And if we could measure several such ratios, then we could maybe even distinguish between several models. Okay, for the second scenario, which we have considered, we have added a 45-dimensional Higgs field as well as a 15-dimensional Higgs field on top of the standard model, on top of the Georgi-Glashow model field content. This 15-dimensional Higgs field allows for neutrino masses via a type 2 seesaw mechanism, while the 45-dimensional Higgs field again allows for gauge coupling unification, and also this an operator giving the ratio 9/2 as well as an operator giving the ratio 2. Okay, how does neutrino mass generation work? So first of all, this is the standard model decomposition of the 15-dimensional Higgs field. So the first entry is the SU3, then SU2, and here U1. And this delta 1 here is actually the triplet which we need for a type 2 seesaw mechanism. So with this new Higgs field, we can write down a Yukawa coupling with the 5-bar Fermian field. And this decomposes under the standard model in these 3 Yukawa matrices. The first one is the one we need for the type 2 seesaw, but on top of that, we get these additional 2 Yukawa couplings. And they are related by a gut scale prediction. Okay. Then to have the type 2 seesaw, we need an additional coupling between the 5-dimensional Higgs field and the 15-dimensional Higgs field. And then we also need a mass term for the Higgs doublet. And under the standard model, this decomposes into these lines. So from the Yukawa term, we get exactly the Yukawa term that we need. And from this trilinear Higgs coupling, we get the trilinear Higgs coupling that we need. And from these terms here, we get a mass for the triplet. Okay, and with this, we can write down the typical type 2 mass. Okay, then another question is, how does the running of the down-type Yukawa matrix and the charged lepton Yukawa matrix, how is this changed with these new Yukawa matrices? We can see this here. So what's particularly important here is that this Y1 speeds up the running of the charged lepton Yukawa matrix, and Y6 speeds up the running of the down-type Yukawa matrix. So if we have a scenario, for example, where this delta 1 has a small mass and delta 6 has a large mass, which means that this would mean that if we run everything down from the gut scale, that delta 1 is much longer in the spectrum. And by this, we would speed up the running of the charged lepton Yukawa matrix and not change the running of the down-type Yukawa matrix. And on the other hand, if, for example, this delta 6 has a very low mass and delta 1 is higher, has a mass close to the gut scale, then we would not significantly change the running of the charged lepton Yukawa matrix, but we would speed up the running of the down-type Yukawa matrix. And with this new freedom, the running for the Yukawa ratios for the third family and second family are a bit more arbitrary. So yeah, so this upper line would sort of correspond to having a small mass for delta 1, and the lower line sort of corresponds to having a small mass of delta 6. And what we can see is that now, on top of the ratio 3/2, 9/2, we have the additional possibility to have a ratio of 2 and 6. Okay. Then let's say we impose this ratio 3/2 and 9/2, or 2 and 6, and we fit everything to the observed data. Then having these two ratios actually allows to have all of these 4 particles light. They are not predicted to be light necessarily, but they are allowed to be light. And if they were observed, they could come from such a model, but they don't have to. The same thing here. We predict these 3 states. We predict these 3 states can be light, but they don't necessarily have to be light. Okay, then what's also interesting is that these 2 models have a different prediction for the gut scale, and this directly translates into different predictions for the Nucleon decay rates. So model 1, or the full 1 sigma HBD interval of model 1 will be tested by Hyperkamiokande, but for model 2, we will only be able to look at a very small part of the predicted parameters of the prediction. Okay, then our last scenario, which we have considered, is a hybrid type 3 plus type 1 seesaw mechanism, and this can be achieved by introducing this 24-dimensional Fermian field. And we again introduce a 45-dimensional Higgs field to allow for gauge coupling unification and also to allow to write down some of these operators. Now it actually turns out that 3 such combinations of Yukawa ratios are viable. Okay. Then how does neutrino mass generation work? So the 24-dimensional Fermian field decomposes like this under the standard model gauge group. Here is the SU2 triplet, and here the complete singlet under the standard model. And this is needed for the type 3 seesaw, and this here gives the type 1 seesaw. Okay, we can write down these terms here. So one coupling between the 5-bar Fermian, the 24 Fermian, and the 5 Higgs, and then the same coupling but with the 45-dimensional Higgs. And from these two Yukawas, we actually get 19 new Yukawas under the standard model, which are related by some Clebsch factors. And these 4 here are used for the type 3 seesaw mechanism plus type 1 seesaw mechanism. And this is then how the neutrino mass matrix looks like. It looks quite complicated, but actually it's just all of these matrices are just rank 1 matrix, and they are connected via Clebsch coefficients because and as a result of this is just a rank 2 mass matrix, which means that only 2 neutrinos are predicted to be massive. Okay, now this scenario also allows to have some light relics. In model 1, actually the triplet, which gives neutrino mass, could be light. Then in model 2, this lepton quark here could be light. And in model 3, also this lepton quark could be light. But now we really predict that this has to be smaller than 100 TeV. And in model 3, it even has to be smaller than 10 TeV. So this is really now a strict prediction. Otherwise, these 2 scenarios cannot work. Okay, then the gut scale is also, we also get very different predictions. This is actually a logarithmic scale. So in model 1, the gut scale has to be smaller than 10 to the 16. However, in model 2 and 3, the gut scale gets very close to the Planck scale. And because of this, the proton decay predictions for model 2 and 3 are very small. So we will not, we should not observe proton decay if model 2 or 3 are realized. Or if we observe it, then this would contradict these 2 models. On the other hand, model 1 predicts quite rapid proton decay, and again, Hyperkamiokande will measure the full 1 sigma interval of this proton decay channel and almost the full 1 sigma HBD interval of this neutron decay channel. Okay, a small summary on these Yukawa ratios. So actually, if we have higher dimensional operators, they can lead to fixed gut scale Yukawa ratios. And we have investigated such fixed gut scale Yukawa ratios in different scenarios. So if neutrino masses are generated by a type 1 seesaw mechanism, we have found that only 1 such combination of ratios works. However, if we have a type 2 seesaw, then there are two possibilities which work, and if we allow for a type 3+1 seesaw mechanism, then there are three combinations of these ratios that could work. Okay, now sort of changing the topic, because so far we have not really talked about dark matter, but there's also a possibility to have dark matter in SU5 guts. And one nice example would be an Axion dark matter. So to discuss this, let's have a look at the strong CP problem. So in the Lagrangian density of the standard model, we can write down such a G dual term. And this theta bar is then a combination of some term in the Lagrangian density plus some term from the mass matrices. Now, since we are allowed to write this term down in the, by the symmetry, we should also do that. But if we write this down, this allows for some phenomenology. For example, it gives a non-zero neutron electric dipole moment. But if we look at the current measurement, this translates into a prediction of this parameter, which is very small. So one question which one can ask oneself naturally is, why is this parameter so small? Is there maybe some nice solution to it? And there are a few solutions. One of them is the Pesci-Quinn mechanism, for which an additional pseudoscalar is introduced, and an approximate shift symmetry is also imposed. And if we have these two assumptions, then this is the Lagrangian, which one can write down. And here we have an explicit breaking term for this shift symmetry. Now, if we have these terms, and we minimize the Axion potential, then it actually turns out that this term exactly cancels with this one in the minimum. And thus, the strong CP problem is dynamically solved. Also, by using Carroll techniques, one can compute the mass of the Axion, and one actually finds that it is inversely proportional to this decay width. Okay, so since the shift symmetry is broken by a dimension 5 operator, one requires a UV solution, a UV completion to it. And one possibility of such a UV completion is the KSBC Accent. So for the KSBC Accent, we take the standard model and we add vector-like quarks on top of it, plus an additional scalar singlet. Now, we also introduce a global U1 symmetry, and we let these vector-like quarks transform differently under this global symmetry. Then this global symmetry can be broken by the scalar field, and after it is broken, this is sort of the expansion of the scalar field, where VA describes the VEF, rho A is the radial part, and A is the angular part. This then turns out to be the Axion. Okay, then with these charges which we have imposed, we can also write down a Yukawa term between the vector-like quarks and the scalar singlet field. And after the scalar singlet field has obtained its VEF, this then translates into a mass term with this additional phase, which depends on the radial part of the scalar field. Now, what one can do to remove this phase is a chiral field transformation, which looks like this. But under this chiral field transformation, the Fermian measure transforms non-trivially, and this introduces exactly this coupling which we had before. Okay, so what we have done so far is we have considered the KSBC case with a simple quark, but in general, this could be a reducible representation under the standard model gauge group, where just one of these SU3 representations needs to be non-trivial. And in such a general case, we not only introduce a coupling of the Axion field with the gluons, but also a coupling with the fermions. This just comes from the fact that the Q is non-trivially charged under SU2 cross U1. Okay, how can we compute this coupling to the fermions? For this, we introduce the QCD and QED anomaly coefficients, and they are just given by group theoretical constants, as well as the charge of the axion under, by the charge under the Pechiquin symmetry. Okay, then another UV completion of the Pechiquin mechanism is given by considering a 2 Higgs doublet standard model plus, again, a scalar singlet. Now, the 2 Higgs doublets transform like this under the Pechiquin symmetry, and the singlet, again, just carries a charge of 1. Now, if we write down the scalar potential, we can write down all these modular terms, and on top of that, a coupling between the Higgs doublets and the scalar singlet. Now, after both the Pechiquin and the electroweak symmetry breaking, we can expand all these fields around the VEF, and the term which we are in particularly interested in is just the VEF multiplied with this phase. Then it turns out that the axion is a linear combination of all of these phases, and also the VEF is a linear combination of all of these VEFs. But in most models, one expects that the VEF V phi is much larger than the other two VEFs, and in such a case, the axion is dominantly sitting in the radial component of this scalar singlet. Okay. Now, looking at the Yukawa terms for this DFSC axion, one actually has two possibilities, how one couples the standard model fermions to the Higgs fields. And the difference is just given by this last term here. One can decide whether one couples it to the down type Higgs or the up type Higgs. Now, after the Pechiquin and electroweak symmetries are all broken, these Yukawa terms translate into mass terms with an additional phase. And we can again do some chiral field transformations to remove these phases here. But by doing this, we again introduce coupling to the GG dual and also to the photons. And here, this E over N, which we had in the KSBC, is given by 8/3. And if we instead look at DFSC2, we would have exactly the same, but the factor 2/3 instead of 8/3. Okay, now the question is, how can we embed something like this into SU5? And this was first done by Weiss, Georgi, and Glashow. They took the Georgi-Glashow model and added an additional U1 Pachiquin on top of it. Then they considered a model with 2 Higgs doublets, and they embedded this scalar singlet into the 24-dimensional Higgs field. Now, in the Georgi-Glashow model, this 24-dimensional was a real field because it's an adjoint, so it can be chosen to be real. But if you want to charge it under the Pachiquin, this has to be a complex field. Okay, then they chose these the U1 Pachiquin charges for all the fields, and by this choice, one can write down these terms in the Lagrangian, and this exactly resembles the DFSC1 model. So that means we have successfully embedded the DFSC into SU5. However, same as the Georgi-Glashow model, the Weiss-Georgi-Glashow model suffers of all these shortcomings. But what's nice in this model is that since the 24 breaks simultaneously SU5 and Pachiquin, that means that the Axion mass is actually directly related to the gut scale, which means if we have such a scenario in a gut and we can predict the gut scale, then we immediately know the Axion mass. Okay, now let's look at a realistic SU5 cross U1 Pachiquin. For this, we took the Weiss-Georgi-Glashow model and we added vector-like quarks on top of it, as well as this 35-dimensional Higgs field. Okay, with these vector-like quarks and the 35-dimensional Higgs field, we can have neutrino masses at the loop level. On top of it, these 15-dimensional Higgs fields contain also a 3-2-1/6 representation, which mixes with the quark doublet of the standard model, and this corrects the Fermian masses. Then we also have an Axion, which is then given by a combination of the DFSC and the KSBC mechanism, because we both have vector-like quarks and 2 Higgs doublets. Okay, how does the Fermian mass correction work? So this is the decomposition of the 15-dimensional Fermian field under the standard model gauge group, and this sigma 3 has exactly the same representation as the quark doublet of the standard model, and because of this, we have some mixing. So that means that the down-type Yukawa matrix is now 4×4, and only this 3×3 upper block is shared with the charged lepton Yukawa matrix. And if we then do a block diagonalization of this 4×4 block, then the 3×3 part obviously gets changed, and this exactly corrects this mass relation. Then for the neutrino mass, they are given by such a loop diagram. And if this is computed, then this is how the result looks like. And this YA and YB are both rank 1 matrices, which means that the full neutrino mass matrix is rank 2, and we have 2 massive neutrinos. On top of it, because the neutrino mass for the neutrino mass generation, we need this YA, and this YA is also needed for the down-type mass correction. the combination of these two effects only allow for normal ordering. So that means this model directly predicts that neutrino masses have to have normal ordering. Okay, let's look at the Nucleon decay predictions. So these are the 2 sigma HBD intervals, and the blue lines are the current bounds, while the red lines are the future bounds of Hyperkamiokande. So what we can see is that Hyperkamiokande will probe part of the parameter space in this particular channel, and it will also probe part of this particular channel. And then what's actually nice is that the ratio of these two channels is predicted to be very sharply, which means if we could observe both these channels, then we could look at the ratio, and we could also compare it with this prediction here. Okay, then the more interesting and more predictive part is actually the Axion phenomenology. So we get a QED, an anomalous parameter of 52/3, and then for QCT we get 13/2. And we get this relation between the Axion decay width and the gut scale. And because of this, we have a direct relation between the Axion mass and the gut scale, and the gauge coupling at the gut scale. So this is predicted, which means that just from gauge coupling unification, we immediately know the Axion mass. And moreover, the couplings of the Axion are also depend on the decay width, which is directly linked to the gut scale. And this means that also these couplings are predicted. Same for the neutron electric dipole moment, also related to the gut scale. So interestingly, there are a few experiments which are planned to be built, which look for such axions. So here in this upper figure, we plot the Axion mass against the Axion coupling to the photons, and the blue line is our prediction. And then this ABD, this means abracadabra. This is a experiment which is planned, and this will actually probe some part of our parameter space in its final state. Moreover, another experiment which is going to be built is dark matter radio gut, and this will probe an even more significant part of our parameter space. This black line here you can ignore because this is just some theoretical, some experiment which is theoretically proposed, but it's not planned to be built yet. Then for the neutron electric dipole moment, there's also an experiment called Casper Electric, which will be looking for this. And this will probe almost the entire parameter space of our model. So this means if we combine both of these two predictions with each other, then the entire parameter space will be probed by future experiments. This is also nicely shown in this figure here. So the points which we have generated here, we have generated them with a Markov chain Monte Carlo analysis, which means that all these points have a very low chi-squared, so they can be almost perfectly fitted to the low energy data. And as we can see, for example, the experiment which looks at the neutron electric dipole moment will probe everything here on the left, and then the two experiments which look for the axion to photon coupling will probe everything on the right. And already the combination of these two kinds of experiments will probe the entire parameter space. But on top of it, a proton decay experiment will also probe a significant part of our model. And if we're lucky and are somewhere here in this region, it would even be possible to probe our model with 3 different kinds of experiments simultaneously. Okay, so the conclusion, if we combine the Pechi-Quinn symmetry with the SU5 symmetry, this leads to a prediction of a very narrow Axion mass range. And this mass window is actually determined by an interplay of gauge coupling unification constraints, partial proton decay lifetime limits, and also the need to reproduce the experimentally observed Fermian mass spectrum. The model, which we presented here, predicts 2 massive neutrinos, which are of Majorana nature, and the entire parameter space of the presented model will be probed by a combination of 3 different kinds of future experiments, looking both for Axion dark matter as well as for proton decay. So that would have been my talk. Thanks a lot for your attention, and I'm very happy to answer questions.
Excellent. Thank you very much for the talk. It was very, very detailed, very thorough, very nice. So we are open for questions. So there is usually a lag between the talk and the time that this reaches YouTube. So let's start with questions from the Zoom audience. I have a couple already, so let me start. So I was wondering, so you use effective operators to devise these flavor ratios, but at the same time you also impose particular structures on your Yukawas. So the question is, what family symmetries are you using for this?
So we have just analyzed these scenarios. We have not constructed a full model at the current point in time.
Oh, I see.
One could use some Q1 factors, but yeah, we have not constructed it at this point.
I see. So what motivated this particular structure, the placement of zeros in specific positions?
Mm-hmm. Okay, so let's look at model 1.
Yeah, that's the one that because for instance, you have in the lower Yukawas, you have all of the entries, and then the upper one, you have the zeros and the 1, 3 and the 3, 1. So initially I thought, oh, this must be a consequence of whatever flavor symmetry they're using. But if you're putting a 0, then it means that there's something that might go wrong if you put a number there. So I was wondering what's going on there.
Yeah. So actually, if you have 0 mixing here, then this is something which we also have worked on in another project. Then you can get some very nice predictions for the PMNS parameters. Okay, for this one also needs to have the Neutrino Mass matrix, but let's say one has these ratios, then one predicts out of these ratios the 1-2 mixing in the charged lepton sector. And if one then has a particular form of the neutrino sector, and for example, tribimaximal mixing or something like that, then one can get predictions for the 2-3 PMNS parameter. Then something which is also interesting is, let's say the uptype Yukawa matrix could be completely real, and in the downtype Yukawa matrix, one could just have I here, just one imaginary entry. In such a case, one out of this immediately reproduces the correct CP phase for the CKM matrix, and one also gets predictions for the direct CP phase of the PMNS matrix. But so this is just motivated by other work, but we have not we've not done such predictions in this particular case.
Right. So in principle, tentatively, you do more than just reproduce the ratios. You also get to reproduce flavor structures. Which is
I mean, this is something which has been done in other works, and we have just analyzed these models, which are motivated by giving such predictions.
Okay. Great. And these effective operators, do you are they easy? I mean, are they straightforward to get from like an ultraviolet completion? Like, can you connect it to SO10 breaks to SU5, and then you would expect these operators to come about? Did you look at these things?
Yeah, this is actually not. If you have SO10. And this is not so easy to get, because then you also have some correlation with the uptype Yukawa matrix, and this is then like you have sort of too many constraints to fit everything. So in SO10 it's not really working. In SU5 it's working very well, because the downtype and charged lepton masses are very similar. The uptype masses are a bit more distinct. But yeah, these operators come out of such. So you have to introduce such fields which have masses above the gut scale.
Right. Okay, great. I don't know if anybody else has got any questions from the audience.
I have a question for Kevin. Kevin, in your slide 41, you were giving mass to the neutrino via kind of loop diagram that is very similar to the scotogenic model, but with multiplets and so on. My question was regarding, is it possible to have any kind of accidental symmetry in this model in such a way that you can have in the loop a neutral and stable particle to be also to take the role of dark matter beside the action, because you were talking also to have action, or in some aspect to action could be the dark matter, but in this case, if you have a massive particle that also is going to be stable and neutral, you can have also dark matter in the wing sense, let's say. I don't know if you have considered also this.
We have not considered it, so I don't really know.
No, because this is the same diagram that you have in these scotogenic models, in which you have in the loop. The loop is protected via Z2 symmetry, let's say the simplest that the people used to have. So in that sense, if one of the particle is neutral and is the lowest with that extra symmetry, it may become dark matter. For the reason I was asking about this specialist diagram that you have here in that slide.
We have not looked into it, so I cannot really answer it at this point.
No. It's just I was wondering if you check that, but maybe later you can see if it is possible in your model. Okay, thanks.
Thanks.
Okay. I have a couple more questions regarding your light relics. So I was, of course, wondering if these relics can affect like electroweak fits, you know, the STU parameters, or maybe contribute to flavor in a way, as you know, this RD anomaly, flavor universality, or anything like it can affect flavor in any way. I don't know if you have checked. Maybe you can have a lepton flavor violation, things like.
Yeah, I mean, for example, this particular lepton quark has been extensively used to explain the RK star anomaly. However, yeah, this is since this is now
we're not talking about that one anymore.
Yeah, that's maybe not the best one anymore. But RD star cannot be explained via these particular letter quark, and would require some different one.
But still, the upper bounds on the masses are not that terrible, right? So in principle, if these things are heavy enough, then you can make them not contribute to anything giving you problems, I guess.
Yeah, this we have. I mean, we also sort of assume. Where is it? Sorry. Okay, sorry. We sort of also assume diagonal texture for the Yukawa matrix, and then we wouldn't have any violation.
Yeah, then it's okay. Yeah. Okay, great. So we did not get any questions from the YouTube audience. So unless, I don't know if Roberto has got any other question.
No, I don't have any other.
Okay, great. So then that would be it. Thank you very much, Kevin, for this very detailed talk. And to all of the audience, we'll be seeing you in 2 weeks with Miguel Romao giving a talk on machine learning, right? So see you soon. Thank you very much for being here.
Thanks a lot for the opportunity.
Okay.